height. And how do we find it's, so I'm just talking to the random STEM people, non-STEM people, which you guys can hear. Well, what's the area here? Area of this thing that's shaded. We go height times width. So I'm thinking maybe this is the way to present integration. Okay, so next thing I know is, okay, that's fine. What if I took this rectangle and put it on the x-axis? So before I go on, so you got into the graduate class for that? Or? Holy. So you need to prep for it. So what is not 1,000, it's 8,000. Oh, wow. Okay. That's messed up. Okay, you need to lock yourself in 16 hours per day during the break. Get ready for that grad class so you can beat the grad students who might not be that great. This is CU Boulder. The grad student quality is not going to be that great. Yeah, because you have suffered through this. It's like this class here. Oh, you volunteered for this class, here's your A. But people don't want to take my A. I've been emailing people, like, just, no, well, that's fine too, but just send me something so I don't have to fail you. They won't even send me anything. I'm like, just fucking send me whatever I send you back to me. Don't even. So this time, 14 people have already turned it in. And then there were people who were late. So that's going to happen again. But I have, right now, for the first exam, got 2 people who are missing. And for the second one, I think I have 4 people who are missing. This is an easy A class. I have 20. So only 14 turn in on the. So then I think people. Yep. Did you remember all the girls who disappeared? Yeah, yeah. Mm. The day one was the least sexy of the yeah, because I was like, oh yes, 2 on days. Yeah. There is no, I mean, I think this class has to be for STEM people. My wife is not interested in a rectangle. Why do I get excited when I see this? Is this something? Why is this exciting? If you put this rectangle and people start clapping in the classroom, they're like, look at him, he stuck a rectangle over there. So when I do this, what happens to the width? Width becomes, this is what happens to the width, right? And then the height of this rectangle becomes this number here. All right. And now, if the area was this, what do you guys think about this presentation? So, Umid, rectangle height times width gets you the area of the shaded region. Then I take this rectangle and put it on the plane on the x-axis. Yeah, it's because only 67%, Gavin only understood 67% of the last stuff. So now I'm going, hey, what's the area now? It is height times width. So height is now this thing. And width is this guy here. Good presentation. Next, what if I had a curve on top of this bastard? So now I have this situation. Okay. And let's say this x1 is actually x naught, and what should I do here? So this would be x naught, xn, and then this would be b, and this would be a. Okay, Umid, now tell me what I should say. What's the next sentence? Or Ryan of Ryan, the two Ryans over there. So we took the height, multiplied by width, we got the area of this region. Then I stuck the rectangle on xy axis, and then the area became this height times this width. Then I went on and I put a curve, a function on top of this, and I dotted this line. So now what should I say next in my great lecture of today? Now I'm interested in the area under the area of the region under the curve, which includes this bit and the area of the rectangle. All right. So what can I say about this right now? Do we have a Riemann sum? Technically, we do. We decided to just use one rectangle. And this rectangle gives us a what, Umid? Sorry, I'm bugging you guys. I'm pretending this is a real class. Very good. Area of the rectangle gives us the approximate area of the region, or the area of the region under the curve. Where's the error, Umid? How did I show error? With what color? Red. Very good. So we have, if this is the Riemann sum, and if I subtract this with L, what does L represent? The actual exact area of the shaded red region and shaded blue region. And what this does is it says that this thing should be less than what? Error. Very good. The error is in epsilon right there. All right. How do we make the error smaller? By sticking in more. There you go. Gavin, don't you understand this? I'm talking to. Isn't it? This should be the way to present integration. Yeah, this is a moment of original thought. Now, so I'm going to stick a second rectangle right here. The error epsilon is shrinking, isn't it? I mean, I could just go home and have some ramen soup. Okay, here we go. So now how do we show the area? Omid, what's the first thing I should write here? Hey, we should put some x here too, right? Let's call this x1. And then should we tag it? So we don't have to deal with, should we use the left-hand point or the right-hand point? We could tag this guy right here. Or maybe we should choose this one, and then I'm choosing this one. How many of these should I stick in here? Two. Very smart. So I stick one and plus another one. Okay. Is the area calculated by this sum better than before? Yes, because epsilon now can be a smaller number. So the difference between the exact area, what's the exact area? The area shaded with blue lines plus the lines in the red. The shaded area with the red lines has now shrunk to just this bit and that bit. And how do I express this more concisely? Using the summation sign. And then we just have this here. All right. And this thing is called Riemann, R for Riemann sum. So the function is here, and these rectangles and the subdivision of the base of these rectangles or the subdivision of the closed interval AB into subintervals is called what? The letter is, what is P? Ryan, this Ryan. The left Ryan. Yeah, for me, you're, no, you are left, yeah. Right lion, sorry. We can't say R in my country. Lion. P stats, no, it's not a super advanced math. We took the closed interval and divided it up into two subintervals. Very good. And if you had taken a tagi, it would be a dotty here. There we go. This thing is the Riemann sum, and it can also be represented like that. This is the Riemann sum. I like today's class. Though I miss Sophia, I like her questions a lot. So by the way, so starting Monday, we'll be just doing what I was doing with you in that. Yeah, so metric spaces and then more sets. So that will be useful everywhere. So, okay. And maybe some apparently probability, modern probability is all sets. You have to be very, very, okay, all righty then. What if I put infinite number of these guys? More and more and more and more and more and more, where you can't even, I put in so many that there's no place for me to go in with my red marker and say, hey, that area is not covered. When that happens, how does that happen? Anybody remember? What do we do with this guy? We take the Riemann sum and go 0 on the width. Is that right? Yep. No, or maybe we go, I have to look. Yes, the number of rectangles have to go to infinity. When they do that, in other words, very good, Ryan of the left, the right. And so here we stick the n goes to infinity. So going from k equals 1 to n, when n goes to infinity, there are infinite number of additions going on. And when that happens, the error between this guy and this guy is less than whatever we have decided, a very small error. It's never the same though. Yeah, even with infinity, there's always this error. You just have to choose it. Because this is magic, this doesn't really happen. But then you're right, maybe it becomes 0. If it became 0, that's what they would put in the definitions. They don't do that. So in the definition, do you find this thing? No, we need to fix that, right? We have to replace that with? So we're going to stick this notation for the approximate sum. Minus the exact sum. And how do we show that the base, the width, how do we show we have infinite triangles under the curve? By saying that the width of the largest, the triangle with the largest, widest base is now less than a very small number. So what's the width of one of these guys? We go. This is saying this is saying that this is the norm of the rectangle with the widest base. And we are going to make sure it is very small. So when this thing goes, and another way informally was what Krantz was doing. He was sending this thing, the norm to 0, just to kind of match with the other stuff. So if you have this situation, then if this is true, and then this is true, then the function has a limit. That is, this function is integrable. And class has ended.